So, in my the last slide of my previous lecture was this slide, and I think we left off where we spoke about the second harmonic generation, and I had said that second harmonic generation is a special case. It happens when the primary wave of frequency omega 2 is absent and only omega 1 is present. So, there is only one primary frequency which is input, which is the input in the crystal or the medium where second harmonic generation takes place, and we go on further with that. So, here if you see the, so we will be concentrating more on the this equation we will be concentrating on this in the coming set of slides. Okay. So, let me go and start with that slide then. So, I had spoken about spatial synchronization and phase matching previously. So, let me explain what I mean by spatial synchronization and phase matching, which is very important for second harmonic generation, for efficient second harmonic generation. Okay. So, here what I give on the left hand side here in this, it is just a schematic diagram of what is happening in my crystal or the material through which I am passing my primary beam or the primary electromagnetic wave that I am passing. So, this is my primary electromagnetic wave. It has a certain frequency omega. Okay, I have shown it in red just to distinguish, and these are the waves which are going through the medium. And as it goes through the medium, as I have said before, it gives rise to the dipole effect, and dipole means there is a shift between the core nucleus and the electrons. There is a shift of the electrons compared to that. So, you have a dipole moment, and dipole moment per unit volume in a particular volume is the polarization. So, I will say that my primary electromagnetic wave has given rise to a polarization in the medium at a certain point, and this electromagnetic wave goes on to different parts of the medium and goes on inducing this polarization, and the polarization itself gives rise to certain secondary waves which may be of this frequency or may be slightly different. By the different ones I have shown in green here, So, polarization itself is giving rise to the primary, it is adding to the primary, it is augmenting the primary, and also creating some newer frequencies. Okay. So, here it goes on to the polarization, and I can call it as a wave, as a polarization wave, because once the beam has entered the medium or the crystal, and it induces this polarization, and the polarization is a tensor, P is a tensor, and so in different directions it starts going as a wave, and it may be different in different directions. Okay, that is why it is a tensor. But for the moment you consider the polarization as a wave which is induced by this primary magnetic wave, and we want to know what happens at the end of the crystal, or as it has traveled, say, from this point to another point Z. Okay. How has the polarization changed? Has the primary wave changed, or what exactly has happened to it? So, I want to put all this explanation that I have given to you in the formula here. Okay. The polarization wave and the electromagnetic wave are propagating with a phase velocity of c by n omega, where n omega is the frequency dependent refractive index. Okay. Keep in mind this, the refractive index of the medium is different for different frequency, which as you know, in any kind of light, when a beam passes through a prism, you get that separation of colors. That itself shows that the refractive index seen by different frequencies is different. So, the frequency is dependent on the refractive index is a frequency dependent entity, all right. So, I will describe my wave, my primary wave, the beam, it is an electromagnetic wave. So, I will describe it as E is equal to E0 cos omega t minus z n by c. Okay. So, it is a travelling wave, t gives that, it is a travelling wave and it is travelling along the z axis. Okay. So, that is why you have this z. And of course, the travel, the velocity is the velocity or the phase of the beam is modified by the refractive index it sees. So, here this is what all that is encompassed in this equation. Okay. And now this wave will give rise to a polarization wave, which you have seen before. Polarization is epsilon chi E, the value of E I am just putting back here. So, you get a wave value for this polarization. Okay. Now, the wave E and P need not have the same amplitude, but will be proportional to each other. Okay. So, we do not think about the amplitude too much. It is not that the P and E will have the same amplitude, they will be proportional. Maybe P will be a little lesser, E will be a little, the amplitude of E0 will be higher than this whole quantity, and so on and so forth. So, in my next equations, therefore, I have forgotten about the amplitude part. I have just written a proportional quantity, because we want to concentrate only on this cos and its argument, this part, the travelling wave part. Now, the secondary wave due to P, which will be created, for example, at 2 points in the medium. Just consider 2 points, Z1 and Z2. When I say the secondary wave created due to P, due to this polarization, what I mean is the secondary wave which will have a frequency omega, same as the primary wave, and it does create new frequencies also, which is 2 omega, which I will deal with later. For now, just assume that P is also creating certain secondary waves with a frequency omega, and the primary wave with frequency omega still remains, and that again is creating new polarization. So, I can say the P and the E are kind of augmenting each other. The energy, there is energy flow between P and E and P, and so it goes on, and that is how it reaches the end of this thing. Okay. So, now I have assumed Z1 and Z2 as 2 different points. At Z1, the field, E field, will be proportional to cos of omega t minus Z1 n by c. Okay. It will be influenced by that point Z1, but it will also be, the wave will be influenced by the distance it is going to travel. So, the distance it is going to travel is Z minus Z1. The final destination is Z. You have started off at the point Z1. Okay. So, I have this term also in the argument. Okay. And of course, it is dependent on the refractive index or modified by the refractive index. Okay. So, similarly for another point Z2, I describe this secondary wave that has been generated at point Z2. So, again that is dependent on the point Z2 or influenced by the point Z2, and also influenced by the distance it is going to travel from Z2 to Z. So, now my argument is this much of the cos term. Okay, if you see these 2 terms, they are similar to this equation. The only modification is because it has been produced at 2 different points and it is a secondary wave. Okay. Actually, the phase part of the wave, this part, the argument of cos omega, this part is the phase part. Okay. So, this phase part of the wave, I have just put it down here, the first one, it comes out to be t minus z n omega by c. So, if you just open it out, again just open out the brackets, and you will come to this t minus Zn n omega c. Both of them are identical. Okay? These two are identical. So, two new secondary waves which were created at point Z1 and Z2 reach the final destination with the same phase as the original primary wave. So, they are kind of phase matched, or they even if it is not exactly the same, they are related to each other by a certain phase which is constant. The easiest way is to think that they are there is no phase difference between the two, which this equation shows here. Okay. So, it can be stated that the various waves at different points of the medium are synchronized or in phase. Okay. So, that is the outcome of this. Okay, now let's see what happens to the waves which are the double frequency or a second harmonic wave. For this moment, we know the primary wave and all those secondary waves, they are in phase. Okay. So, let me go to the specific term, and we will come to the reason why phase matching condition is required. Everywhere you will see in books or wherever, phase matching is a very important criteria for second harmonic generation. So, okay, let us go back to the second harmonic generation polarization wave can be defined as this. If you go back the previous 2-3 slides, you will come across this formula which we have seen before. Okay. P2 omega, that means double the frequency, is given by epsilon 0 chi 2, it is a second order occurrence, and this is the amplitude E01 and cos 2 omega t minus kz. K is the wave vector given by omega n by c, and n is of course the refractive index at frequency omega. Now, just see by analogy the wave produced at points Z1 and Z2 can be described by this formula. Okay. So, in the previous slide we had said the waves, the secondary waves produced at Z1 and Z2, and that time I was referring to say this and this. Okay. But now these were of the frequency omega. Now I am referring to this green waves. I have shown it specifically as green because generally for near infrared wavelengths, when they are frequency doubled, you get in the green region. Not only that, it is just to distinguish between these two different kind of secondary waves. So, you assume that these are 2 omega waves. Okay. Now, they are also being produced at points Z1 and Z2. So, in an analogous way, I can write this kind of equation for my green waves. Okay. That is exactly what I have done here. So, I have called it, this is frequency doubled wave. So, E1 at point Z1 for 2 omega, it is a function of Z and T, will be proportional to of course cos, and here it will be 2 omega because it is a 2 omega term, 2 omega frequency, T minus Z1 n omega by C, Z minus Z1 n 2 omega by C. So, even the second harmonic wave is influenced by the point Z1 where it is created and influenced by the distance it is going to travel, Z minus Z1. Okay. And at point Z2 again similarly, the secondary wave at 2 omega is influenced by the point Z2 and also the distance between Z1 and Z2 and Z. Z is my final destination. The wave is traveling along Z, and all this wave that is traveling along Z, there are different points in the medium which are adding these secondary waves, and they all reach the final destination Z. Now, I want to know what is the phase of all these small secondary waves that are reaching the point Z. how do they look like? What does the phase of those secondary waves are like? Okay. So, all the wave formation at Z1 and Z2, these waves propagate with the velocity c upon n to omega, okay, which is different from the velocity of propagation c upon n omega. Okay. So, the refractive index that this wave sees is n2 omega, and n2 omega is not the same as n omega, which the primary wave was seeing. The primary beam was seeing a refractive index of n omega, while this secondary wave is seeing a refractive index of n2 omega. So, obviously, the velocity becomes different for this wave. Okay. So, now what do I do? Now, you just take this argument, put it here. Similarly, take this argument and put it here. Just open up the brackets and make it look a bit neat and nice. And I have only substituted delta n is equal to n omega minus n2 omega. Okay. This is one refractive index, this is another refractive index, and the delta n is the difference between these two, and I have put it out here. Wherever n omega, n2 omega occurs, I have put it as delta n. Basically, I am just rewriting this argument of cos, rewriting in this form. So, again in case of Z2 also, the point Z2 also, I am rewriting it, and I have introduced the term delta n. Okay, substitute this thing back into this equation here. I have substituted it back, E1 2 omega, you just put all that and this is what it will look like. Okay. E2 omega, again it will be cos 2 omega t minus Z2 delta n minus Z n2 omega by c, here also Z n2 omega by c. By comparing these last two equations, it can be seen that the secondary waves arrive at point Z and augment each other only if delta n is equal to 0 or n omega is equal to n2 omega. See here, if I put delta n equal to 0, this whole term disappears, and if you see what remains is both of them have the same phase. The waves that originated from Z1 and the waves that originated from Z2, both of them have the same phase, and it happens only when delta n is equal to 0. Okay. And this is what we call as a phase matching condition for frequency doubling. Now, when all the frequency doubled waves have reached that point Z and they are in phase, if and only if delta n is equal to 0, then only all these will be transferring the energy within each other, and you will get a final very intense beam. And only when this phase matching occurs, that primary beam has been able to transfer its energy to the secondary frequency doubled beam, only when delta n is equal to 0. So, this is the condition, and that is what we want in generation of second harmonic beam. We want the primary beam to convert all its energy into the secondary beam. We want an intense second harmonic beam. That is our aim. Okay. And it can be done only when phase matching condition is achieved. So, you understand why the phase matching condition is very, very important in order to get an intense second harmonic generation. Okay. Now, so what I have done here in this previous lecture is, previous slide, is that I have considered 2 points, Z1 and Z2. Okay. Now, instead of considering 2 points Z1 and Z2, as the beam is traveling through the crystal, there are so many Z1 and Z2 points. So, I have to find the final intensity, I must take the integral of all these points which are generating this second harmonic. Okay. So, how do I do that? So, I will have to integrate it. So, let me see, analogous to the last two equation, we can write analogous to this and this, E1 and E2, the electric field strength for radiators between Z1 and DZ1. Okay, I just take a small strip. Instead of calling it Z1 and Z2, it is a small strip of Z1 and DZ1. It has changed by DZ1. And I can write the electric field, the small electric field due to that small stretch is d 2 omega Zt is equal to A. A is a constant, it is say an amplitude. Okay. I have just introduced this term A because I was taking proportionality constant all the time. Now, I have put an equal to sign. So, I have put in A, which is the amplitude. Okay. Cos of 2 omega t minus Zn 2 omega by C minus Z1 delta n by C dZ1. Okay. This is at point Z1, but it is travelling a small distance of dZ1. Okay. And the wave is given by d E2 omega. Okay. It is exactly the same as that. I have just written it this way so that we can take a integral. So, the field strength of the secondary electromagnetic wave at point Z, once it comes to Z, will be the sum of all this, and A is a constant. So, you have to take an integral. You take that integral from 0 to Z, cos of 2 omega t minus this term dZ1. Okay, it looks like a big integral, but it can be done very, very easily, integrating by the method of substitution. So, the argument of cos 2 omega I will just substitute here by x. So, minus delta n by x dZ1 is equal to dx. Okay, I just put it back here. Okay, now it looks like a simpler integral, and the integral is just integral of cos A is sin A. So, here I have sine of 2 omega x. I will put back that x once again, A C upon all this, just substituting, plain substitution. I have put it back and it looks like this. Okay. Now, I must do it between 0 to Z, okay, all these small points between 0 and Z. So, I will have A of this sine of this term minus sine of this term. Okay. So, make it look a bit more simpler, or so that I can interpret the result very easily. I just use a trigonometric term identity, trigonometric identity, which is you all know it, sin A minus sin B is equal to 2 cos A plus B by 2 and sine of A minus B by 2. Okay, you must be knowing it. So, I will just use this identity and I come to this value. Okay. So, this is my final equation, which is a multiplication of a cos term and a sine term, all in 2 omega. Okay. So, I have this equation. Now I can interpret this equation well enough. Okay. So, it is a function of z and t. What I find is this term, I can take it out as the amplitude term. Okay. Here. So, here it is, E2 omega zt is equal to this term. I have just taken out the sine square term here and I have kept the cos square term here. Okay. So, this term, as you can see, it has a t and a z. So, it is travelling, it is a travelling wave and going along the z axis, and this total term is the amplitude. Okay. Now see the funny part about this amplitude. This amplitude originally, if only A were present, it would have been constant, but then it has a sine term. That means it is an undulating amplitude. The equation shows that the secondary electromagnetic wave has a double frequency 2 omega and it has a varying amplitude. The variation of the wave amplitude propagating through the medium. So now what do we have? When we have added up all this, taken the integral, and we find it has come to the end of that z, the particular distance that we require, it has a varying amplitude. Okay. Now we have to think about what this varying amplitude means. It's a travelling wave, it's going there, and it has a varying amplitude. So in my next lecture, I will be talking about the finer details about the varying amplitude, and again we will see how the phase matching condition becomes absolutely important for second harmonic generation. Okay. So we've already seen that before. You do need second harmonic a phase matching condition, delta n is equal to 0, and here again at this point you will realize from a different angle that second harmonic generation, for second harmonic generation, you need delta n to be 0.